Hello dear students, good evening. Today is the second session of linear programming problems, and before I proceed further, could you please confirm that you are able to view the screen properly and able to hear my voice very clearly?
Yes, sir.
Okay, great. So now in the previous session, if you recall that we concluded with a method called corner point method. Okay. In the previous session, we discussed about a problem. That problem is that a furniture dealer to sell his chairs and table to have maximum profit. Okay. So we have seen that how a convex polygon has been constructed and how we found the different points in the different vertices of that convex polygon. So now its more generalized version is the corner point method. So these are the steps of the corner point method. Dear students, so first what I want to do, I want to briefly describe this method, and after that we will solve some problems. When we solve some problems, you will get the exactly how this works, and then again if you revert back to the method, the steps, you will completely realize. Means in simple terms, what I can say, first first we will look into by solving some questions, and after that we will understand what is the corner point method. That will help us to understand the method very well. But briefly, let me tell you this one. This method comprises of the following steps. Okay, so what is the first step? First step is that find the feasible region of the linear programming problem and determine the corner points, that is the vertices, either by inspection or by solving the two equations of the lines intersecting at that point. Okay. Second step is that evaluate the objective function z equal to ax plus by at each of these corner points. Now, if we get uppercase m and lowercase m respectively denote the largest and smallest values of this point. So we are assuming that capital M, the uppercase M, is the largest value and lowercase m is the smallest value. Now the step number 3 says that when the when the feasible region is bounded, capital M and that is uppercase M and lowercase m are the maximum and minimum values of z. You see, dear students, in step 2 we have assumed let uppercase m and lowercase m respectively denote the largest and smallest values of these points. So there we defined largest and smallest. But here what we are saying, here in this case we are saying is that the maximum and minimum. So there is a slight difference between the largest and maximum and smallest with minimum. There is a slight difference, and that I will describe you. There is no such difference if the feasible region is bounded. Then capital M, which is the largest value, is becoming the maximum value, and similarly the lowercase m, which is the smallest value, become the minimum value when the feasible region, that is the convex polygon, is bounded. Now it may possible the feasible region is not bounded, means if it is unbounded, then there are two cases. The first one is that in that case m is the maximum value of z if the open half plane determined by ax plus by greater than m. Ax plus by, by the way, the objective function. Now we get another inequation, that is ax plus by greater than m has no point in common with the feasible region. Otherwise z has no maximum value. This particular statement I know that you are not able to understand. That's what I said, that we will solve some questions and then we will revisit this particular steps, especially for unbounded region. And the point number B is that similarly, if lowercase m is the minimum value of z, means lowercase m is the minimum value of z if the open half plane determined by ax plus by less than lowercase m. Ax plus by is the objective function expression, that ax plus by less than lowercase m has no point in common with the feasible region. Now, if there is a point common, then we can say z has no minimum value. Okay, we will solve it by few questions. Now, without wasting any time, let us go to solve few questions. So, I have a plan to solve 5 questions. Let us see how much we can do today. Okay. So, the first question I am going to give you here, dear students. The first example. Okay. So, we need to solve this linear programming problem, and obviously whatever the solution we are doing here, it is using the graphical method. So, here we need to solve, means we need to find the maximum value of 4x plus y, that is why it is maximize 4x plus y. Let me use a different color, let me use blue color. So, we need to find the maximum value of 4x plus y subject to the constraint. The first constraint is that x plus y less than equal to 50. Second constraint 3x plus y less than equal to 90. And fourth one, that is the non-negative constraints, that is x greater than equal to 0 and y greater than equal to 0. So, what we will do first? First we will first we will construct the straight line corresponding to these inequations. So, whenever it is written x plus y less than equal to 50, so we will draw the straight line x plus y equal to 50. So, let me explain with one problem in details. The same concept will be applicable to the other problems. Okay. So, if you see x plus y equal to 50 will be a line which I am drawing in the blue color. Okay. As you see it here, just a minute. Okay, let me draw it more properly. So, in the blue color I am drawing the line x plus y is equal to 50. Now, according to our constraint, it is x plus y less than equal to 50. When it is less than equal to, what we will consider, dear students, we will consider the left hand side of the straight line, x plus y equal to 50. So, this is the region, whatever I am drawing in the blue color straight line. Okay, this one. Now, the second one is that 3x plus y greater than 3x plus y less than equal to 90. So, let me use a red color. 3x plus y equal to 90, first we will draw. So, what is the straight line? This is the straight line 3x plus y equal to 90. So, you know how to draw a straight line in the coordinate system. Okay. Now, here also it is less than equal to 90. As it is less than equal to 90, that means we will consider left hand side of the straight line. Okay. Fine. Now, the next two constraint, that is x greater than equal to 0. X greater than equal to 0 means what, dear students? So, if I describe into the green color, what is x equal to 0? X equal to 0 is nothing but the equation of the y axis. So, that is x equal to 0, whatever I have marked in the green color. Now, x is greater than equal to 0. Greater than equal to 0 means is now we will consider the right hand side, this region. Okay. This is the right, greater than equal to 0, that we consider the right hand side. Correct. Now, the next one is that is that y greater than equal to 0. So, let me do it in the pink color. What is y equal to 0? It is the equation of the x axis is y equal to 0. Now, as it is y greater than equal to 0, that means it should be in the top one, right? Got it? Okay. Now, as all these constants has to be satisfied at the same time, our feasible region will be the region where all these 4 line segments actually overlap. That is the blue line segment, the red line segment, the green line segment, the pink line segment. Okay, all has to be at the same simultaneously at the same time overlap. So, what will be that region? If I mark this in the black color, it will be this region. This region, if you see, it will be the overlap with all this one. So, that is why it is mentioned the shaded region. So, if I underline, the shaded region is the following, in the following figure is the feasible region determined by the system of constant 2 to 4. Okay. So, let me undo all this straight line and then so that you can look into the feasible region more properly. So, let me quickly undo drawing all these straight lines. Okay. Now, let me go through this statement. The shaded region is the shaded region in the following figure is the feasible region determined by the system of constant 2 to 4. That is the system of constant, that is 2 to 4. This is. Now, we observe that the feasible region OABC is bounded. So, as it is bounded, so we can have the maximum value of the objective function for x plus y. So, we now use the corner point method to determine the maximum value of z. So, what does it mean? First, we need to find the coordinates of these points. Okay. First, we need to find the coordinates of these points. What are the points? The coordinate of the points where all these 4 lines x plus y less than equal to 50, x plus y equal to 50, 3x plus y equal to 90, x equal to 0, y equal to 0, where they all intersected. So, if you see, they intersected as these 4 points O, A, B, C. Now, we need to find the coordinates of this point. So, you can find the coordinates of this point very easily, by solving any 2 equations. You can find the coordinates of this point. For example, O, to obviously we know it is the origin. Now, if for A we know it is on the x axis, so its y coordinate will be 0. So, 3x plus y equal to 90. From this equation, we need to find the value of x by keeping y equal to 0. So, obviously, we will get x equal to 30. Similarly, to find the coordinates of the point B, we need to solve these 2 equations, that x plus y equal to 50 and 3x plus y equal to 90. So, if we solve these 2 equations, we get the value of x equal to 20 and value of y equal to 30. So, that is why we get the coordinates of the point B as 20, 30. And in the similar manner, we find the coordinates of the point C as 0, 50. So, how to find the coordinates of the point C is that we find that x plus y equal to 50 is the equation of the straight line, and a point C on the y axis is having x coordinate 0. So, in this equation x plus y equal to 50, we should apply x equal to 0 and we get the value of y is equal to 50. So, the coordinates of the point C is 0, 50. Now, what we need to do? We need to find the value of the objective function, that is 4x plus y. If I mark into the green color, that is the objective function 4x plus y. So, that value we are finding for all these corner points. Okay, that means for 0, 0, when x equal to 0 and y equal to 0, we get the value of the objective function as 0. when x equal to 30 and y equal to 0, that is 30 comma 0, at that corner point which is associated with the point A, we get the value of the objective function, that is 4 into 30 plus 0, that is 120. For the third point B, that is 20 comma 30, we get the value of the objective function 4x plus y as 4 into 20 plus 30, that is equal to 110. And finally, for the point C, which is having coordinates 0 comma 50, we find the value of the objective function 4x plus y as 4 into 0 plus 50, that is 50. So now among all these values, that is 0, 120, 110 and 50, we see 120 is the maximum value. So that is the maximum value of the objective function. So what we get, dear students, we get the maximum value of the objective function z as 120, and that value obtained when x equal to 30 and y equal to 0. So that's what we have written here. Hence the maximum value of z is 120 at the point 30 comma 0. I hope this is absolutely clear. Now I took some time to explain you this example 1, because all the other examples what we are going to solve today, it will be based on that, and there I will go little quickly. Okay. Now let me go to the second example. Okay. So let me take it from my slide. Okay, dear students, so if you look into the second example, so what is mentioned here, solve the following linear programming problem graphically. We need to minimize z equal to 200x plus 500y, that is our objective function 200x plus 500y, subject to the constraint. The first constraint is that x plus 2y is greater than equal to 10, 3x plus 4y is less than equal to 24, and x is greater than equal to 0, y is greater than equal to 0. So that means in simple terms we need to find the minimum value of 200x plus 500y subject to the inequations x plus 2y greater than equal to 10, 3x plus 4y less than equal to 24, x greater than equal to 0 and y greater than equal to 0. So for that, what we will do, first we will draw the straight line x plus 2y equal to 10, and this is the straight line x plus 2y equal to 10. So this straight line means, if I can say, this is the straight line x plus 2y equal to 10, and the second straight line is 3x plus 4y equal to 24. So this is the second straight line, 3x plus 4y equal to 24, and x equal to 0 is nothing but the y axis, and y equal to 0 is nothing but the x axis. So we have all these 4 lines. Now as 2x plus y is greater than equal to 10, so that means we should consider all the right hand side points. Okay, so 2x plus x plus 2y is greater than equal to 10, so that means we will consider all the right hand side points here. Okay, all these right hand side points. Just a minute. X plus 2y greater than equal to 10, like this. Okay. Now the next one is that 3x plus 4y less than equal to 24. That means we should consider all the region in the left hand side. This one we will consider. Okay. Just a minute. It will be up to this point, like this. And then obviously x greater than equal to 0, y greater than equal to Now we need to find where all these 4 inequations actually overlap. That means the region where the blue line, the red lines, and and the lines corresponding to x greater than equal to 0 and y greater than equal to 0 overlap, and that is the region. If you see that, region ABC. So let me undo drawing the straight lines, then you will get that is the region ABC. Correct. Now we find the coordinates of the point A as 0, 5, coordinates of the point B as 4, 3. So this is A, this is B, 4, 3, and coordinates of the point C as 0, 6. So how we find the coordinates of the point A? Very simple. The equation, corresponding equation is 2x plus 2y is equal to 10, and there we will apply x equal to 0 and we get the value of y equal to 5, so 0, 5. Similarly, we find the coordinates of the point B by solving the equations x plus 2y equal to 10 and 3x plus 4y equal to 24, and we get the solution as x equal to 4 and y equal to 3. So that is the coordinates of the point B. In the similar manner, we find the coordinates of the point C, that by solving that equation 3x plus 4y equal to 24, and there we will apply x equal to 0. So we get y equal to 6. So we get the coordinates of the point C as 0, 6. So we get the coordinates of all the 3 points ABC. Now the same thing we will find what is the values of the objective function z for all these 3 points. For the corner point 0, 5, we get the value of the objective function z, which is 200x plus 500y as 200 into 0 plus 500 into 5, that is 2500. For the next corner point 4, 3, we find the value of the objective function as 200x plus 500y, that means 200 into 4 plus 500 into 3, and this gives us a value 2300. And finally, for the third corner point 0, 6, we find the value of the objective function 200x plus 500y as 200 into 0 plus 500 into 6, that we get the 3000 for this point corresponding to 0, 6. Now among all these 3 values 2500, 2300 and 3000, we get the minimum value is 2300. So that is the minimum value of the objective function z. So we get the minimum value of z is 2300 attained at the point 4, 3. That means when x equal to 4, y equal to 3, we find the minimum value of the objective function, and the value is 2300. I hope it is clear. Now let me proceed to the next example. So dear students, so next example I am going to place it here. Okay, so here the question is that we need to find the minimum and maximum value of the objective function 3x plus 9y. Okay, so we need to, you see here, minimize and maximize z equal to 3x plus 9y subject to the constraint x plus 3y less than equal to 60, x plus y greater than equal to 10, x is less than equal to y, and x greater than equal to 0, y greater than equal to 0. So we need to draw all the straight lines. So x plus 3y equal to 60. So this is the straight line x plus 3y equal to 60. Next one is that x plus y equal to 10. So this is the straight line x plus y equal to 10. Next one is that x less than equal to y. For that we have first drawn x equal to y. So that is x equal to y. So x less than y, it should be less than equal to y should be the all the left hand region of the with respect to the straight line x equal to y, and then x greater than equal to 0 and y greater than equal to 0 is quite obvious because it is all the positive values of x and y. Now if we plot all these if we draw all these straight lines and then we find the overlapped region, we will get the overlapped region as A, B, C, D, with point A having the coordinate 0, 10. Okay. So point A is having the coordinate 0, 10, point B is having the coordinates 5, 5, point C is having the coordinates 15, 15, and point D is having the coordinates 0, 20. So you see, dear students, so that become the A, B, C, D, correct? So that is the point. We found that one, the coordinates of this point. So using the corner point method, we need to find the value of the objective function 3x plus 9y for all these corner points. So now for the first corner point, that is A having coordinates 0, 10, we get the value of the objective function z equal to 3x plus 9y as 3 into 0 plus 9 into 10, that is 90. For the second corner point B having coordinates 5, 5, that is x equal to 5 and y equal to 5, we find the value of the objective function 3x plus 9y as 3 into 5 plus 9 into 5, and it gives us the value for the point B as 60. For the corner point C having coordinates 15, 15, that means x is equal to 15, y equal to 15, we get the value of the objective function 3x plus 9y as 3 into 15 plus 9 into 15, and it is 180. And finally, for the corner point D having coordinates 0, 20, that is x equal to 0 and y equal to 20, we get the value of the objective function z as z, which is 3x plus 9y. So we get the value as 3 into 0 plus 9 into 20, that is 180. So as we need to find both minimum and maximum value, so what we get, dear students, is that for all these 4 values we get the minimum value as 60 and maximum value as 180, and maximum value obtained for multiple values of x and y. So when x equal to 15 and y equal to 15, we get the maximum value 180. When x equal to 0 and y equal to 20, then also you get the maximum value 180. Okay, so we get the solution. So now if I go through this particular statement which I mentioned in the bottom, we now find the minimum and maximum value of z. From the table we find that the minimum value of z is 60 at the point B 5, 5 of the feasible region. The maximum value z on the feasible region occurs at the 2 corner points C 15, 15 and D 0, 20, and it is 180 in each case. That is the maximum value. Now there is a special point to mention here, that I mentioned as remark in the whatever I mentioned in the blue color here. So what is the remark? As you see, there are multiple optimal maximum solution, maximum value, that the maximum value is 1, that is 180, and that 180 obtained for multiple value sets of x and y. So you see that for the point C having the coordinates 15, 15, we get the maximum value, and also for the point D having coordinates 0, 20, we get the maximum value. So then what we can say? We can say that any point on this line segment, from C to D, providing the maximum value. That means there are infinitely many values of x and y for which we get the maximum value 180. And what are those infinite values of x and y? Those are the values those are the coordinates of the points in the line segment CD. And that's what I have mentioned here in the remark section. So let me read it out. Observe that in the above example, the problem has multiple optimal solutions at the corner points C and D. That is, both the points produce same maximum value 180. In such cases, you can see that every point on the line segment CD joining the two corner points C and D also give the same maximum value. Same is also true in the case if the 2 points produce the same minimum value. Okay. So, in this case we have found the maximum value, but if the same situation arises, that means for multiple coordinates, for multiple corner points we get the same minimum value, then if we join that line segment for those two using those two coordinates, all the points on that line segment gives the same minimum value. Okay, I hope it is clear. Now let me proceed to the next example, that is example number 4. Okay, dear students, so let me bring the example 4. Okay. So now what we need to find? We need to find the minimum value of the objective function minus 50x plus 20y. So let me use a different color, green color, let me use the blue color. So our objective function is z equal to minus 50x plus 20y. We need to find the minimum value of this objective function subject to the constraints. So there are 4 constraints. The first one is 2x minus y greater than equal to minus 5. Second one is that 3x plus y greater than equal to 3. Next one is 2x minus 3y less than equal to 12, and the final one is x greater than equal to 0, y greater than equal to 0. So in simple terms, we need to draw the straight line corresponding to all this. For example, 2x minus y equal to minus 5, so that is the straight line. Second one is that 3x plus y greater than equal to 3, that is the straight line. Next one is that 2x minus 3y is equal to 12, that is the straight line. And finally, x equal to 0 is the y axis and y equal to 0 is the x axis. Now if we find, we will see that we get the feasible region is something like this. That is the feasible region, and here the feasible region is unbounded, it is not bounded. That means whatever I described in the previous session is that it cannot be enclosed within a circle. Okay. So then what to do? I am going to explain you, listen very carefully. So dear students, first of all, let us graph the feasible region of the system of inequalities 2 to 5. Okay, 2 to 5, the inequalities whatever I mentioned here. So we have graphed it. The feasible region, the feasible region which is shaded is shown in the following figure. Okay. Observe that the feasible region is unbounded. We now evaluate z at the corner points. So we get the corner points as 0, 5, 0, 3, 1, 0 and 6, 0. For all these 4 points, we found the value of the objective function, that is minus 50x plus 20y, and these are the values we have obtained. Fine. Now what is our objective? Our objective is to find the minimum value. Now among all these 4 values, 100, 60, minus 50 and minus 300, we get the smallest value as minus 300. See, here we are using the word smallest, not minimum. Why? Because the feasible region is unbounded. If the physical region is bounded, if the feasible region, not physical, if the feasible region is bounded, then we can say that minus 300 is both smallest and minimum, in case you can see it is a minimum value. But as the feasible region is not bounded, that is it is unbounded, we can say minus 300 as the smallest value. Now whether this minus 300 is going to be a minimum value or not, for that we need to do something extra. And what is that extra? That I have explained here in this paragraph. So dear students, from the table we found that minus 300 is the smallest value of z at the corner point 6, 0. Correct? Minus 300 obtained when x equal to 6 and y equal to 0. Now can we say that the minimum value of z is also minus 300? Note that if the region would have been bounded, the smallest value of z is the minimum value of z by means of theorem 2, which we described in the previous session. But here we see that the feasible region is unbounded, therefore minus 300 may or may not be the minimum value of the objective function z. Now to decide this issue, that means whether it is a minimum value or not, we need to bring another inequality, that is minus 50x plus 20y less than minus 300. Okay. So minus 50x plus 20y is the objective function and less than minus 300, because that is the smallest value, minus 300. So we bring that inequality. So to bring that inequality, what we get, we first find the straight line. So that is the straight line. This is represented by the straight line, that is minus 5x plus 2y equal to minus 30, because minus 50x plus 20y less than minus 300 means minus 5x plus 2y less than 30. So now as it is less than 30, so it will be in the left hand side. So now and check, so that is a separate thing, but what you get, the straight line description of minus 5x plus 2y is less than minus 30. Now we need to check whether whether the resulting open half plane has points in common with the feasible region or not. If it has common points, then minus 300 will not be the minimum value of z, otherwise minus 300 will be the minimum value of z. Let me repeat once more. Okay. What we need to check? We need to check whether the resulting open half plane, whatever we have found earlier, okay, has point in common with the feasible region or not. Okay. If it has common point, then minus 300 is not the minimum value. It is the smallest value, but not the minimum value. Now if there is no common point, we see that minus 300 will be the minimum value. Now what is our observation? Our observation is that if you look into it in the above diagram, we get common point something like this, right? So what we say, as shown in the above figure, it has common points, therefore z is equal to minus 50x plus 20y has no minimum value subject to the given constraints. Now in case the example that z equal to minus 50x plus 20y, we need to find the maximum value, okay, that is the 100 or not at 0,5. For that we need to do solve the inequality minus 50x plus 20y greater than 100, and that you can do the exercise and do let me know how you found. Okay, I hope you got it. Now let me go to the next example, the example 5. Now before I going to the example 5, so I will suggest you, after going to all this thing, now you can revisit the corner point method, okay, whatever I mentioned earlier. So let me go to the corner point method. Okay, so this is the corner point method. Now you can revisit that corner point method at your own time, at your own space, and then you will realize that you understand the steps involved in the corner point method very well after discussing all these 4 examples. Okay. Now dear students, we are going to go for the 5th example. and I'm going to show it. Let me take it from my presentation. So here what we do, dear students, is that we need to find the minimum value of the objective function 3x plus 2y subject to the constraints. What are the constraints? First one is that x plus y greater than equal to 8. Second one is 3x plus 5y less than equal to 15, and x greater than equal to 0, y greater than equal to 0. So as you know that we need to draw the corresponding straight line in the coordinate section. So first one is that x plus y equal to 8. So this is the straight line x plus y equal to 8. Second one is that 3x plus 5y equal to 15. So this is the one, 3x plus 5y equal to 15. Next one is that x equal to 0, that is the y axis, and the other one is that y equal to 0, that is the x axis. So we have drawn all the 4 lines. Now x plus y greater than equal to 8. So greater than equal to 8 means what, dear students? So it will be, we will consider all the region in the right hand side. Greater than, no, that's why it is right hand side. So this region, whatever I marked in the blue color. Next one is that 3x plus 5y less than equal to 15. So let me mark into the green color. So 3x plus 5y equal to 15 is this straight line, and at it is less than equal to 15, so we will consider all the left hand side of this straight line, 3x plus 5y equal to 15. Now next is that x greater than equal to 0, y greater than equal to 0, that means the region in the first quadrant. Now what we see, dear students, is that we see, once we draw the graph of the inequalities 1 to 3 as shown in the following figure, from the figure we can see that there is no point satisfying all the constraints simultaneously. In fact, there is no point common between the green line and the blue line. So thus the problem is having no feasible region, hence no feasible solution. So we cannot solve this problem. That is also, so that's why I bring this example 5. I hope it is clear. Now dear students, so let me summarize that exactly how we are going to solve this problem. So what is the summary? Let me show it to you. Okay. So from the examples, the 5 examples whatever we have discussed today, so from this example, so what we have observed, and that I am going to place it here. So dear students, so from the examples which we have discussed so far, we notice some general feature of linear programming problem. What is the first one? The feasible region is always a convex region. What is convex region and what is concave region, that I explained in the previous session. The class recording of the class is available in YouTube. You can look at it. Second one, the maximum or minimum solution of the objective function occurs at the vertex corner of the feasible region. Okay, that we have seen, that is called the corner points. Third one, if two corner points produce the same maximum or minimum value of the objective function, then every point on the line segment joining these points will also keep the same maximum or minimum value. So this is the remarks what we have understood from the corner point method. Now with this note, we are about to conclude the session for today. Now before we finally conclude, I would like to just give a indication for the next session, that what are the different types of linear programming problem, which we are going to solve in the next session. Okay, and all are based on the same corner point method whatever we have described today. Okay, here today what are the 5 problems we have done? There we have mentioned x and y. So in the word problems, so there will be some a proper meaning of this x and y. So what are the few important linear programming problems? The first one is the manufacturing problem. So in the manufacturing problem, what we will do, dear students, in this problem we determine the number of units of different products which should be produced and sold by a firm when each product requires a fixed manpower, machine hours, labor hour per unit of product, warehouse space per unit of the output, etc., in order to make maximum profit. That is one type of problem, that is called the manufacturing problem. Second one is the diet problem. So what is the diet problem, dear students? In these problems we determine the amount of different kinds of constituents or nutrients which should be included in a diet so as to minimize the cost of the desired diet, such that it contains a certain minimum amount of each constituents and nutrients. That we will see in the diet problem. Third one is the transportation problem. So in transportation problem we determine a transportation schedule in order to find the cheapest way of transporting a product from plants or factories situated at different locations to the different markets. And finally, we will discuss about the allocation problem. Allocation problem, in these problems we determine allocation of resources, for example land, in order to find the maximum production, say crops, with least usage of say pesticides. So all these different type of problem will be fall into the same category and we will using the same method, corner point method. So all these things we will be discussing in the next session in details. So with this note, let me conclude the session here, dear students. In case you have any comments or any question, never hesitate to let me know. Do you have any question, dear students?
No, sir.
Okay. All right. Thank you very much. We will see in the next session. Okay. Thank you. Bye.
Thank you, sir.